Picture a modern recommendation model at YouTube scale. It's a transformer, much like a language model, and it takes in a prompt describing what a user has watched, who they are, and what candidate video we're considering scoring. The obvious way to feed this transformer everything it needs is to just turn every signal into text. The user watched a video with semantic identifier A100, B100, C100, and so on, for 8 tokens per video, plus the watch completion ratio of 5%, plus the watch time of 50 seconds, plus the channel name, plus the device type. Do that for 200 history items and you've blown past 1,000 tokens before you've even said anything about the candidate. That is the problem this paper from Google tackles. The core tension is that these large recommendation models, or LRMs, need traditional recommender signals like dense floating point features and sparse categorical features to compete with the classical, large embedding models that came before them. But textualizing everything creates absurdly long prompts, and long prompts mean quadratic attention costs, huge memory footprints, and slow training. Prior work like Longer, GenRec, and HyMiRec has tried to compress user history by merging every K items into one representation or by using shortened semantic identifier codes. But those methods mostly compress item identifiers and ignore the rich interaction features attached to each item, like how long the user actually watched that particular video. The proposed solution is called token factory, and the key idea is to treat traditional signals as a new modality, similar to how a vision language model treats images. Instead of tokenizing features into discrete vocabulary indices, Token Factory produces what the authors call soft tokens. A soft token is just an embedding vector living directly in the transformer's input embedding space, produced by a small learnable neural network from raw feature values. Think of it like this. Rather than describing a wine by writing out a paragraph of tasting notes for the model to parse, you hand the model a single pre-computed flavor vector that already lives in its native representation. No tokenizer, no vocabulary lookup, just an embedding. The architecture is built from modules called token makers, and each token maker is responsible for a slice of the input. In the video recommendation setup, there are 3. A watch history token maker that turns each watched item and all its associated interaction features into soft tokens. A query token maker for user-level features like age and region, and a candidate token maker for the video being scored. Inside a token maker, all the raw features for one item, things like the semantic ID embedding, the channel name embedding, the client info, and the watch duration, get concatenated into one big vector. Then, a differentiable function, usually just a multi-layer perceptron, but potentially a small transformer, projects that concatenated vector into a fixed number n of output embeddings of the model's hidden dimension. That n is a knob. Set it to 1 for simple features. Set it to 10 for long sequences you want to compress heavily. Crucially, this projection network is trained end-to-end jointly with the main recommendation model, so the soft tokens learn to align with whatever semantic space the transformer wants them to live in. A few design choices are worth calling out. Because query and user-level features are static across all candidate items scored in a single request, their soft tokens can be pre-computed once and cached, which is a real serving latency win. The prompt length becomes deterministic regardless of how many raw features you add, because each token maker outputs a fixed budget of soft tokens. And when you want to compress a very long watch history further, they offer 2 options. An MLP applied across the sequence dimension that squashes n tokens down to m, or an attention pooling scheme borrowed from prior work where you summarize every K items with a single learned token. Now, one concern with replacing textual semantic IDs with a single soft token per item is that you lose subtoken attention. When each video was 8 discrete tokens, the transformer could attend to the fine-grained pieces across different history items. With 1 soft token per item, that fine-grained attention disappears. The authors address this in an appendix by showing that cross-item attention patterns remain healthy, meaning the compressed representations still let the model reason about relationships between watched videos. The experiments cover 2 tasks: a ranking model that predicts click-through rate, built on a 110 million parameter Gemini encoder variant, and a generative retrieval model that predicts the next video's semantic ID, built on a 210 million parameter Gemini decoder. On ranking, the baseline uses 1,536 tokens of prompt containing 200 watch history items, and Token Factory compresses that same information down to 480 tokens. At equal batch size, the Token Factory version starts slightly behind on area under the ROC curve, because the newly initialized token maker parameters need to learn from scratch, but by 1.5 million steps it catches up and matches the baseline. When they use the efficiency savings to triple the batch size, the Token Factory model actually outperforms the baseline from very early in training. On the retrieval task, the results are more striking. Prompt length drops from 768 tokens to 256. Training runs roughly 200% faster. Offline, recall at 10 improves by 2%, and in a live A/B test on YouTube homepage recommendations, unique impressions jumped 16.8% overall and 67.1% for videos less than a day old, all while nudging satisfied watchers and satisfied watch times slightly positive. That fresh video result is the most interesting finding. Because Token Factory lets the model efficiently consume more signal per item and reach further back in user history, the retrieval model discovers a much wider pool of candidates, especially newly uploaded content that the baseline struggled to surface. Ablation studies confirm that both the soft token representation of watch history and the inclusion of traditional dense and sparse features matter independently for quality. There are limitations worth noting. Soft tokens sacrifice interpretability entirely, since you can no longer inspect the prompt as human-readable text. The initial training lag suggests these token makers may need careful warm-up or pre-training to work well at smaller scales or shorter training budgets. The paper also does not deeply explore how soft tokens behave when the underlying feature distribution shifts over time, which is a real concern in production where features drift constantly. And while cross-item attention is shown to remain healthy, the loss of sub-token granularity could matter more for tasks requiring finer semantic reasoning than click prediction. Now let's walk through some questions you might have after hearing all of this. Why do soft tokens work at all? When they skip the tokenizer entirely, the transformer never actually cares whether its input embeddings came from a vocabulary lookup or from a neural network projection. What matters is that the embeddings live in a space where attention and the downstream layers can extract useful patterns. Because the token maker is trained jointly with the transformer, gradient descent naturally shapes those soft tokens to be useful, effectively teaching the model a new modality just like vision language models learn to consume image patch embeddings. What would happen if you just used more aggressive text compression instead, like shorter semantic IDs? You could shorten the text representation, but you would still pay the cost of running each token through the full transformer stack, and you would still be constrained by a discrete vocabulary that has to be learned and stored. Soft tokens sidestep both problems by packing arbitrarily rich continuous information into a single embedding, so a floating point watch completion ratio doesn't get quantized into a bucket and doesn't consume its own token slot. Why does the Token Factory model start out worse in the ranking experiment before catching up? The token makers introduce fresh, randomly initialized parameters, including new embedding tables for sparse features that the baseline didn't need because it was reading them as text. The baseline can lean on the pre-trained language model's existing ability to parse textual features immediately, while the treatment has to bootstrap its projection layers from scratch. Once those parameters converge, the more efficient representation wins, but there's a warm-up cost that's worth budgeting for. For large-scale recommendation systems, the practical implications are substantial. Retrieval and ranking stacks at platforms serving hundreds of millions of users are almost always bottlenecked by serving latency and training throughput, not model capacity. Token Factory's pre-computation and caching of user and query soft tokens maps directly onto the standard two-tower serving pattern, where you want to compute the user representation once per request and then score many candidates cheaply. The deterministic prompt length is also a big deal for production, because it means your latency budget doesn't blow up when a power user has 10,000 watch events instead of 200. Perhaps the most exciting angle is what the fresh video result implies. Freshness and cold start have always been painful for retrieval models because new items lack the interaction history that collaborative filtering relies on. If Token Factory's efficiency gains let you push much longer user histories through the model and consume richer per-item features, the model can build a stronger notion of user intent that generalizes to items it has barely seen. That's a lever many recommendation teams would trade a lot for, and it suggests the right way to think about soft tokens is not just as compression, but as a way to buy back capacity that you then spend on longer context, richer features, or larger batches.